Hello everyone. Today I want to talk about regulated cascode or GM boosting and how to understand this circuit. The approach that I'm using here is mostly based on intuition and not calculation and mathematics or um, the conventional way that you can find in books and papers. Uh, so you know that a common gate circuit has a low input impedance, some sort of. If we assume that the RO here is low, so here is sorry, high, so we can say that the input impedance is 1/GM. But if the RO is not high, we would have the effect of the load. So how we can increase the input impedance? In some application we like to have a low input impedance. So how to lower the input impedance is one of the specification or characteristic of regulated cascode. So you can show by equation, writing down lots of equation, that if you add an op amp here, if you add an op amp here, the input impedance is decreasing. So, but intuitionally you can see that when this point is going up, as this is a inverting op amp, this point goes down, and you can see that kind of this configuration over here is a source follower. So when this goes down too, and the regulated cascode and the feedback kind of suppress the changes in the voltage, and based on the Ohm law you can see that when this is just like approximate approach to understand this phenomena, but when this one is increasing and this one stays steady, this means that the input impedance is decreasing. So this is a regulated cascode or GM boosting, and I think oh sorry, and I know Razavi has use equation and everything. I looked at the book, and he used the introducing GM to see the phenomena and how the GM increased, and the reason is that GM is increasing in this case. You can easily sorry, you can easily add like a source here and calculate V in over I in. You can notice that the V gate source of this this transistor is could be V in or let's say, I forgot to mention here, I assume that the gain of the op amp is minus A, so the gate source is be in oh, okay, let's clean all the things. And so the gate source is this term, and we know the GM gate source is minus I in, and you can easily see that V in or I in is GM, and so in this case actually we increase the GM, and this is the reason we have lower input impedance. One thing kind of nice to notice here is because we increase the input impedance, sorry, we increase the GM. So the thing that we can notice is I want to clean up some part of this. These parts maybe. So assume that we didn't have the op amp. What is happening here when we look at the R out? Over here we know the R out approximately is GM of this transistor, RO of this transistor, and RO of and I'm gonna remove this part, and RO of this current source. Let's call this 1, 1, and this 2. So when we add regulated cascode, what is happening is the GM is increasing to a GM RO 1 RO 2. So we increased the GM, we boosted the GM, and this is the reason that we using regulated cascode we can have also a higher output impedance. This is very important, so we can use it in both ways to have a high output impedance or lower input impedance. But forgetting about the equation and everything and just rely on the on our analog kind of intuitional approaches, we can say when this part is going up and through the feedback we know these parts go down, and using and through the transistor also, I'm gonna show that in another color. So through the transistor also this part is going up. It's a common gate, so the output is going up, and when the signal is coming from this way it is going down, and because the input impedance is close to 0, so we can assume that this part is ground, and we do not have source degeneration. So when this goes down the output goes up, and we have like two paths that increase the output voltage. So back to Ohm's law, when we have an increase in the voltage, we can say that we have an increase in the impedance, and this is an intuitional way to see that the output impedance is increasing using this circuit. I'm gonna delete all of this stuff and clean it up. So we have regulated Cascode. The, oh, the up amp. And one good thing about this configuration is when you have like a sensor at the input, assume that you have an optical sensor like a photodiode or something, you can use the up amp bias and bias the input of your photodiode. This is very common in some optical and medical applications that they have a sensor, they need a low input impedance, they use regulated cascode, and also they bias it through this configuration, and they can control the bias, and maybe by controlling the bias inside the chip they can change the configuration of like the characteristic of the sensor. This is kind of amazing that you can program inside and change a sensor that is mostly from in other die, and you can control it. Maybe you like to have lower gain or in the sensor, or you want to maybe increase the gain or lower the gain to have less noise or something like that, so you can control it from the inside. This is very good point to notice if you work with those applications. Also, one thing to notice here is that when you have an feedback you have a feedback in your system, you always need you should always be concerned about the compensation. So maybe you should add like a resistor here for compensation if you have this concern. This might kind of degrade some specification of the circuit, but it should be noticed. But for example, for my PhD exam, I had this question, actually exactly this question from one of the jury members, to how compensate for this circuit, and there are papers about that. But one thing that you can have in mind if you're designing a front end for a sensor, add a photodiode again. So maybe the parasitic capacitor of this photodiode is very huge. Some of them, some photodiode like silicon photomultiplier has depend on their specification, they might have a parasitic capacitor over 200 picofarad. So in these cases and in this situation, because the input capacitor is very high, you might dealing with a single pole kind of a circuit, and maybe compensation would be unnecessary. But I will add some papers about how to compensate for this kind of a circuit. Another thing nice to mention is as you can see, having an op-amp might add complexity and power consumption. So some researcher, what they do is to use a transistor, like something like this. Again, sorry for my drawing. Oh. So they add a transistor here, so still they have the feedback, but they use a transistor over an op-amp. But one problem with this, nice to notice, is that this configuration is kind of a high voltage. Okay, why? Because you have the overdrive of this guy, you have the gate source of this guy, and the gate source of this guy. So you have which is plus VOD. It's kind of a high voltage, and you need a high voltage supply, which is not very popular nowadays, or not available nowadays. Deep submicron. One way to address this problem is to use transistor again, but change it. And this way you can add some sort of a common gate here, and my drawing is not very good, I'm sorry about that. And here you remove the you have a low voltage circuit. As you can see now, you have one overdrive and gate source, and this guy, for example, or over this pass you have the overdrive, gate source, and the other overdrive, and this pass is also one overdrive and a gate source. So you have a low voltage configuration here. I'm just thinking what else to mention about this circuit. Oh, one nice thing about remember one thing, and I had a video about that. When you I'm gonna draw it. Okay, I'm gonna draw it again. So remember, always remember that when you have a current source, it is always appreciated to use the GM of this guy, and for the signal to increase the gain or lower the input impedance. So never leave the current source without adding it through the signal path. Always recycle this, and one way to do this is, so this is the current source. You can bias it over here, bias the circuit, and then take the signal back here. So now you have two feedback paths, and you can decrease the input impedance more than before. So if this is input, so I'm gonna show you this. So this goes up, up, down, down. This is one pass, and the other pass is when this guy is going up, this guy goes up, come back here, and as this is a simple common source, this guy goes down, and it's kind of suppress the change in the input voltage. This is very good way to address the input impedance, and you can easily copy the signal over here and add this is a kind of a current amplifier. I'm just thinking what else to mention, and I think I do not have anything else to mention. And this is the way that you can use the regulated cascode GM boosting. As I mentioned, there are papers about the compensation, so I'm gonna add those papers to the description of this video. But it is very valuable to notice when you have internal feedback in your system, like this one and this one, you should always consider, not consider, but you should be concerned about and pay attention to the compensation. So also you can see you have a feedback in this part. We added the feedback, so we should be concerned about this compensation. In a paper that I'm going to share, they added a capacitor here and they showed that this kind of a help for the compensation of the circuit. There is nothing else to mention. However, there is a paper that I write, the paper, I'm the author of the paper, that shows you can add a dummy actually here at this node, and however you, by adding this dummy, you decrease the GM of this one and you make this feedback path less effective, but you can reduce the DC at the output. The DC current is going to this transistor, DC current, and you will have less DC current here, and you can increase the sizing between this transistor and this transistor, increase the gain, because the gain here actually is will be defined by the sizing between these two transistors, like, and we can call them M2 and M3. These two are the main player in defining the gain in the system. And as you can notice, these two are the gain is defined by the ratio of the sizing of the transistors, which is a very linear thing, and by kind of a good layout you can have a linear system here, that the gain is defined by n. This is very important to notice. You define the gain of the system by the sizing between the two transistors. I'm gonna add some stuff here and explain this more deeply. So M2 and M3, which have the sizing ratio of n, define the gain of the system. So the gain is linear, and in this kind of a system, maybe you do not need feedback to linearize the gain and to remove the effect of the nonlinear component inside your amplifier. The effect of nonlinear component inside your amplifier on the gain of the system. So you would have a gain with dependent on of the GM of the transistor or R of the transistor. It will be defined mostly by the gain, by the size ratio between M1 and M2. But one thing that I didn't mention here and should be mentioned, that so we know when we copy this the signal, also we have the effect of the drain source of the transistor. They play a role. So one way that you can address this is to add the regulated cascode, kind of to define the drain source of the two transistor. So you can have something, for example, like this. Oh, I made a mistake over here. So So you can define it like this. Sorry for my drawing. So these 2 points, because it's an op amp, they have the same voltage, so you kind of you kind of define the drawing source of this transistor by the op amp. And also you can be a little bit more greedy and, for example, add a cascode here and then do the same and kind of define the voltage of these two transistors by two using an op amp. So yeah, this is regulated cascode, and all of this good thing about it. As I mentioned, you can add the cascode to increase to increase the output impedance if you are greedy, or make the drawing source of this 2 point the same. These 2 point the same. Also, there is a paper, I'm remembering stuff now, that they use another method. They kind of create a DC here for these two to make their current the drawing sources are the same. I'm gonna share that paper too. They added like a DC, floating DC here, so these 2 point will have the same voltage, and this is another way to use it. Thank you for watching this stuff. If you have a question, you can email me easily. You can find me on internet by searching my name, or you can comment. Most of the time I forget to respond to the comments, but I always respond to emails and also to messages on LinkedIn. Thank you.